All right. So in today's lecture, we start doing something which is called laser Doppler velocimetry. Now, this lecture notes are courtesy of Professor Cameron Tropia, my long-term collaborator, and he's one of the pioneers of this particular technique, the laser Doppler velocimetry. And so this particular, talk takes heavily from his lecture notes in a workshop that he covered at IISc. So let's do it and see that what we have for laser Doppler velocimetry. So flow visualization, and we will do several of them. One is, of course, particle image velocimetry. So you can have tracer-based velocity measurements. That means you put something into the medium and you start visualizing the flow field. So in this case, for example, this is an aerofoil, and what we have done is, or what the experimentalists did, they put some tracer particles. It could be sawdust, it could be many things, anything. And basically this follows the flow, and using scattering measurements, we are able to see how the streamlines looks around this particular aerofoil, which is very important when we actually try to design aerofoils for, say, aeropropulsion or aerodynamics. Now, this is qualitative. So this roughly shows that, okay, there is a flow, and then there is a separation, and you get a vortex being shed over here, but you really do not know what is the velocity and what is, for example, derived quantities like vorticity and stuff like that. So this can be done using, say, for example, PIV, where we actually try to get that what this velocity vectors would look like, what will be their magnitude, what will be their direction, and also derive quantities like, here, as well as vorticity. So this is a tracer-based velocity measurement, extremely, high throughput, and this is what we are going to cover in the PIV. So the method of measuring velocity is basically it comes in two flavors. One is direct measurement of velocity. That means you know how much distance the tracer or any parcel of fluid actually covers in a particular amount of time delta t. You basically resolve this displacement into the xyz directions, and then the ith component of the velocity is nothing but the displacement in the ith direction divided by the time interval that has elapsed. So this time interval could be very short, so that essentially you go to an instantaneous velocity calculation. It's almost like calculus for you, like dxt. So in this way, you can calculate all components of the velocity. This u1, u2, u3 means x, y, z. So it can be this can be, and put it as ux, ui, and uz as well. So this is more like calculus. Now, in order to measure, so this is a direct velocity measurement, and sometimes it's doable. And then there is vorticity measurement. So this measures the rotation of a fluid parcel or a particle. Okay. And so as it measures, so you can see these are the cross derivatives. So this is the derivative of uk with respect to the other coordinates. There's a variation of u with respect to, so if it's the x component of the velocity, it's a variation with respect to y and with respect to z. In this case, of course, you need to know the slope. That means you need to know the change in velocity over very small distances, because you can see this as a differential. So this is a vorticity. So this calculates the rotation of the fluid particle. Okay, so these are more direct measurements. So there are other things also. So there are, we will cover, for example, the hot wire anemometry part we will cover. But initial measurements were all done with pitot tubes. This is something that is very well known. When we cover the hot wire anemometry, we'll cover a little bit on the pitot tube as well. But the hot wire anemometry was also an extremely potent measurement technique, and it is still used, and very, very good measurement technique as well. It can come in constant current as well as constant temperature. We will cover more on this in a separate lecture. Then, of course, the invention of lasers, which is the laser is the acronym of light amplification by stimulated emission of radiation. So this changed the scenario quite a bit, because now we could have this very coherent lights, which could be used for, for the measurements that we are going to show. So this led to the development of laser Doppler velocimetry in the 1960s, Ye and Cummins in 1964, and in the 1980s, the more field-based measurements, which is particle image velocimetry, came into the picture. Remember, laser Doppler velocimetry is still a point-based or a small volume-based measurements. Particle image velocimetry is more of a field measurement, the kind of field that you see over here. This is like a particle image velocimetry. All right. So the comparison of the different techniques will be as follows. So for point measurement, you have pitot tube, hot wire anemometry, and laser Doppler anemometry, or LDV. Okay, and the whole field, which is basically kind of measurements like this. You can have also have PIV, then variations of PIV, which is tomographic PIV. Tomography we already saw in the Schillerine. And then magnetic resonant velocimetry, which is also, for biological, if you want to measure something in your heart, for example, that would be a good technique to follow. So these are whole field measurements. Then, of course, there are intrusive measurements like pitot tube and hot wire anemometry. These are intrusive in the sense you are physically putting a physical probe into the measurement volume. And what it does is that sometimes the presence of this particular element, though they are kind of can be made very small, they actually disturb the flow field in a non-trivial fashion. And then there are non-intrusive point measurement techniques as well, and field measurements. Of course, this LDA PIV, because they use lasers, they are kind of the ones that are kind of considered to be non-intrusive. So for both probe-based as well as for field-based. The LDA PIV are non-intrusive tracer-based methods. The volume concentration of the particles is less than 1 million part per million. And so LDA is a time is a time shift type of a measurement. We will see that in for a known displacement. So you know the displacement, you measure the frequency shift, and that's how you get the velocity. And we will see how this is being done. PIV is, however, done for the particle displacement for a known time. So you fix the time over which, or basically fix the delta t over which you want to measure, and you calculate the particle displacement, and more in line with what you saw over here. Of course, not this easy. So once you do that, you will get the field measurement. So it is like taking two pictures, and you know that how much these particles have shifted between two pictures, and you know the time duration that has elapsed between the capture of these two pictures. As a result of that, once you divide this delta x by delta t, you should get the velocity. Of course, easier said than done. Okay, LDA, on the other hand, you fix the the measurement volume in space. You have a fixed displacement, and you calculate the time, or in this case, the frequency shift, to know what is the velocity of the particle. Okay, so in one case, delta t is fixed; in the other case, delta x is fixed. Okay, so this is how these techniques actually work. So there are various comparisons, the kind of resolutions that you can get. You have Doppler global velocimetry, you have filtered Rayleigh scattering, you have global phase Doppler velocimetry, you have interferometric particle imaging, and LDV, of course, which we are going to cover over here, then laser flow tagging, then laser transit velocity, then phase Doppler, and then planar Doppler velocimetry, then particle image velocimetry, and then particle tracking velocimetry. All these things happens in a spatio-temporal fashion. As you can see that the field measurements will have the space and the time. The point measurements will have more resolution on the time than on the space. So each technique has got its own advantages and disadvantages, and is also tailored for what you are actually trying to measure. So that is the part that is very important, what you are trying to measure and what is the kind of information that you need. So in one case, you can have very high temporal resolution. In the other case, you might have very high spatial resolution. And some cases, you may need to see the field information. You need to see the entire flow field and how it evolves over time. In some cases, you may be interested in a particular location, and you might want to see what is going on in that particular location at a very high frequency. That means you measure the velocity at a very high fidelity. All these things are possible, and depending on what you are trying to do, these things varies quite a bit. Okay, so the techniques, there is no one one silver bullet for any particular applications. So in the case of tracer based methods, the flow velocity is measured indirectly by measuring the velocity of the tracer particles or the groups of particles. Okay, so in no case, for example, in the first, if you look at this slide once again, okay, these are tracer particles which we expect are following the flow field, but they are not exactly measuring the flow field per se. What it is doing is that it is measuring the velocity of the tracer of the seeding particles or groups of particles, and it is not exactly measuring the flow, but the flow velocity, we are inferring it from the velocity of the tracers. So the selection of these particles is basically then a compromise. You should first have two real situations. One is that the particles should follow the flow. That means this requires small particles and the particles which are density matched with the carrier fluid. That means small particles means they have smaller inertia. As a result of that, when there is a sudden acceleration in the flow field, for example, these particles should be able to follow that flow field without much of a time delay. And the particles should scatter light well, because unless they scatter, you cannot have sufficient measurement intensity. So in that case, as we will see, that larger particles are obviously preferable. And we also need large differences in the refractive index between the particle and the fluid. Okay, so these are the two caveats when we do any tracer based methods. Okay, so when we do light scattering, so the light scattering from small particles, okay, depends on a multitude of things. First is the relative refractive index, that means particle to the medium. So if we call that M, it is the ratio of NP by NF, which is NP is the particle, F is the fluid. Okay, so it's a ratio, it's a relative refractive index. It depends on the particle size, which we just now we will see when we do a little bit of an optics. That means the particle size is given as d. Okay, the particle form and shape and orientation, these are also important, and the light polarization and observation direction is also important. So the scattered intensity can be increased, because we want more of the scattered intensity, by choosing suitable particles and increasing the laser intensity. Otherwise is that if you increase the source intensity, crank it up, obviously the scattered intensity is also going to go up. And we choose also suitable particles for the job. So these are all measurements prerequisite when you are dealing with tracer particles in the flow. It sounds very, when you are trying to get quantitative information out of this, these things matters a lot. So for spherical particles with a diameter larger than the wavelength of light, that means dp is greater than lambda, then the Lorentz-Mees scattering is applicable. This is one of the exact solution of the Maxwell's equation. So for spherical particles with a diameter which is larger than the wavelength of light. All right. So let's look at it this way. So these are plotted all in polar coordinates, and these are particles of different sizes, and then there is an incident beam with a particular wavelength. Now, if the particle is roughly about, say, 20% of the diameter of the wavelength of the beam, okay, it will scatter light in this kind of a fashion, where the direction of illumination is from this direction. Okay, so this is how it will scatter. Okay, if the particle size is the same as the wavelength, this is the scattering diagram that you see. These are all plotted on the logarithmic scale. And when the particle is about 10 times higher than the wavelength, okay, so say for example a laser wavelength is 532 nanometer. Okay, so this will be around 532. This will be 532 into 10. Okay, which means like nanometer, so it goes into the micron range, 5 microns. This is of the order of half a micron, and this is basically very, very small. This is about 20%. of the wavelength of the laser, roughly 1/5. Okay, so this is the polar diagram of the scattered intensity as a function of the scattering angle. So these are the different scattering angle. Okay, so this is 0 scattering angle. You can see this is the most, and these are of course 0 and then 90 degrees. So these are the angles at which you can observe. Okay, so this intensity is shown on a logarithmic scale. So this is how things get scattered. So in the Lorentz-Mean theory, so what happens is that when the particle size is greater than lambda, that means the droplet diameter or the particle or the tracer diameter is larger than the wavelength, which say 532 nanometer is one example. Okay, so you can see that this is the light scattering by about 1 micron oil particle in air. So you can see that 180-degree scattering is like this, and 0 degrees. So the light is coming in this direction. This is basically your oil particle or oil droplet in air. Okay? So the laser wavelength is about 532 nanometer, which is the most commonly used Nd:YAG laser that you have. Okay? So in the logarithmic scale, the neighboring lobes differ by factors which are more than 100. So the neighboring lobes differ quite a bit. So the Lorentz-Mean theory works with dimensionless particle size, which is given as xm ndp by lambda, known as the Mean parameter. So this is the Mean parameter. So this is nothing by pi dp, which is one way of saying it is the circumference or the circumference or the perimeter of the particle divided by lambda. Now, if xm is large, then the scattered intensity ratio forward to back scatter also increases, as you can see. Okay, and the mean scattered intensity scales with xm square. Okay, so as you can see over here, this is the light scattering by a 10 micrometer oil particle. So you understand this, that if we kind of have a non-dimensional number, now if dp is much larger than lambda, so that means xm is also large, then the scattered intensity forward to backward scatter also increase. Okay, forward to backward scatter also increase. Okay, and the mean scattered intensity scales as square of this particular parameter. Okay, so this is the Lorentz-Mean theory in a nutshell. So in the Lorentz-Mean theory, if you look at it, this is the scattered intensity in arbitrary units, and this is the Mean parameter, which is xm, the one that we defined over here, nothing but the perimeter divided by the wavelength of the incoming laser. You can see, and this is the scattered intensity. Okay, and this on the top, you have the particle diameter. Okay, for example, as you can see, the scattered intensity is a function of the Mean parameter. Okay, for a water droplet in air, where this lambda of the laser or the light is about 500 at a scattering angle of 30 degrees. So the 30 degree is the scattering angle. So all these scattering angles are given over here. Okay, so you can see that how the intensities actually change. So for a large particle size, or a large Mean parameter, okay, or xm, okay, you have a very high scattered intensity and kind of falls off pretty rapidly as you go down to smaller and smaller particle sizes, which also leads to a smaller Mean parameter, because there's just that lambda, just that pi and lambda, pi by lambda is a factor that is multiplied over here. So you can see that there is quite a bit of, in a logarithmic scale, you can see that it goes like this, and then it kind of tapers off very fast. And from here to here, we have like 6 orders or 5 orders of change. From a droplet particle diameter of 0.1 micron all the way up to, like, say 10 micron, we have a drop in almost 10 to the power of 6 or 10 to the power of 5, in the scattered intensity. So this is the kind of a thing that we are talking about. All right. So this is, for example, this is German. So this is light scattering, as you can understand. So this is scattered light from a 1 micron glass bead in water. Okay, this is scattered light from a 10 micron glass bead in water. Okay, and this is the scattered beam from a 30 micron glass bead in water. Okay, so you can see that how this, and also remember this statement that when xm is larger, then the scattered intensity ratio forward to backward scatter also increases, And this is exactly what you also see over here. Okay, so this is not trivial. So you go down in the caveat is that you need to decrease your particle size if you want the particles to follow the flow. But it also comes with the caveat that your scattered intensity also drops pretty rapidly. So you have to operate at a region where there's an optimization. That means you have an optimal scattered intensity of light, and at the same time you have a sufficiently small particle diameter or tracer diameter which can follow the flow field without any lag. Because if there is a lag, then you are unable to measure the flow field properly. That means the tracer velocities that you are going to measure is not going to be representative of the flow field in any way. So this curve is therefore becomes very important, that how much loss you have when you go from like 0.1 to 10. So this is like 2 orders change in the particle diameter leads to almost 10 to the power of 5 uh, change, and actually more than that, 10 to the power of 5 plus change in the light intensity, or there is a decrease, go down to smaller and smaller particle size for a particular laser, okay, laser beam, okay, and on a relative basis. So if you see that these are the different seeding particles for gas flows, we have titanium oxide, titanium dioxide. The dP is less than 1. You use an Nd:Ag laser, which is roughly 10 millijoules at 20 nanoseconds pulse width. Okay, and these are the different, light sheets that we make. So oil smoke, for example, has about 1. This is what normally people use in very crude applications. You use a ruby laser, which is at a 5 millijoules pulse. So you can see that this is quite high. And then you actually have, corn oil, which is about 1 to 2 microns. And then olive oil. Olive oil is also very regularly used in flow measurements. Titanium dioxide is usually used for measurements, where, for example, in combustion application, for example, because oil will vaporize. DHS is also something used, which is routinely used in many measurement techniques, and water droplets also. So it depends on what kind of application we are actually looking at. So this is more on. You can also use things like microspheres. You can also use hydrogen bubbles. You can use polystyrene. You can use even fluorescent particles, routinely used, for example, in a variation called micro PIV. You can use phosphorescent polymer dye, lots of things, and these are the corresponding laser types that are routinely used, and these are the corresponding references where you can find more about these applications. And these are particular attention is with the droplet sizes. The particle sizes, like it's more or less in the micron and in the orders tens of micron kind of a range in most of the applications when you seed the flow. All right. So these are, for example, the glass particles used in liquid flows, as you can see. So these are the magnification and different magnifications. You can see that how this flows actually look, how this glass particles look like. So the choice of your tracer particles, keeping in mind this, as well as the just go to this, and then the particle should follow the flow. These two parts are the most important parts when you go for these kind of measurements. So how you do this is basically you can also use seeding generators. So one such thing is called a Laskin nozzle. So the Laskin nozzle works by feeding air into a fluid through a series of Laskin nozzles at almost sonic speeds. So each nozzle produces these micro bubbles, about 1 micron. These bubbles reach the liquid surface and they collapse and they create what we call these micro droplets. And these micro droplets, so they collapse on the surface and they create these micro droplets. And an impact plate is used to filter out the large ones. The number density can be matched, and these micro droplets are then actually fed into the main flow. So these are usually olive oil in an airflow, which is very routinely used. In even research work that we do, we use olive oil a lot. So Laskin nozzle is a very commonly used technique that is used for generating these micro droplets, which are used for seeding the flow field. Just a little bit thing on the laser. So the laser is as we can see, is of paramount importance when you do all this kind of measurements, either PIV or LDV. So this is light amplification by stimulated emission of radiation. So this is an inversion problem actually. So how does it differ from a normal white light? It has coherence, it is polarization, and it's monochromatic, it's highly focused, high intensity, and we can do extremely short pulse lengths in time, which is essential for measuring high-speed flows, for example, because there you need really small pulse width, because you need a stroboscopic type of an effect. So in order to achieve that effect, your pulse width for the laser during the time the laser is lasing has to be very small. Okay, so this is what monochromatic white light actually, what white light actually looks like. It has got all kinds of wavelength. The intensity is typically distributed in a fashion like this. Okay, then you have the laser light, where all of them are kind of phase matched, and you have an intensity which is across a particular wavelength. So it is very narrow. Though it seems like a line, it has a little bit of a width mainly because of lots of non-radiative decay processes. But compared to a white light, this is very sharp. So this allows us to focus the laser and send it over long distances and do a lot of manipulation. Okay. So the demands on the light source for LDV, laser Doppler velocimetry, is that it needs to be monochromatic. It needs to have a spatial and temporal coherence, and should be linearly polarized, and it should be well focused. So this is what a collimated beam of light actually looks like. Okay, this is actual light. This is the dotted line is the desired profile, and so this is parallel light with very small deviation. And the lasers also exhibit something which is called a Gaussian intensity of the beam. So this is how the intensity actually varies across the beam diameter, across the beam cross section essence. So these things have to be kept in mind. So the demand for the LDV is therefore very simple. It needs to have that monochromatic, so single wavelength, and then the spatially and temporally coherent should have, this collimated profile should have very small deviation with respect to each other. So in the next class, we will take more on this.